Welcome back, dear all. In our next session, in this session we are going to see a numerical on displacement, velocity, acceleration and jerk of the follower moving with simple harmonic motion. So in this lecture we are going to see the calculation of velocity, acceleration and jerk of the follower, and similarly the plotting of displacement, velocity, acceleration and jerk of the follower moving with simple harmonic motion. So let's see the numerical. A cam with minimum radius of 25 mm is to be designed for a knife edge follower with moving with the following data. So one thing you should remember here, if you are solving a numerical in which you have to plot displacement, velocity, acceleration graph, but you need not to if you are not going to plot the cam profile, then whether it is a knife edge follower, roller follower or some other followers, it doesn't matter in the numerical whether it is knife edge follower or some other type of follower. Then you need not to bother about which type of follower it is if you are going to solve the numerical on displacement, velocity and acceleration and jerk diagrams when the follower moves with different types of motions. So type of follower doesn't matter here. And similarly the cam with minimum radius of 25 mm, it also doesn't matter when you are going to plot only the graphs, but this will matter and this will be important when you are going to plot the cam profile for different followers or your minimum radius of cam. It will be required then, but in this numerical this data is of no use. To raise the follower through 35 mm during 60 degrees of rotation of cam. So 35 mm is the displacement of the follower, S is given now. 60 degrees of rotation of the cam, so outstroke angle is given as 60 degrees. Next 40 degrees are dwell, so dwell angle is given, and return stroke angle is also given as 90 degrees. So the angle done during return stroke is 90 degrees. Dwell during the rest of cam rotation, so remaining angle is dwell. So if ascending and descending of the cam takes place with simple harmonic motion, that is SHM, draw displacement, velocity, acceleration and jerk diagrams if the cam rotates at 150 rpm. So the angular speed of the cam is given at 150 rpm. So the important data over here is the displacement of follower 35 mm, outstroke angle 60 degrees, dwell angle of 40 degrees, return stroke angle of 90 degrees, and the angular speed of the cam, that is 150 rpm. These are the important data, as well as the type of motion is simple harmonic motion of the follower. So first part is drawing of displacement diagram, as it is somewhat lengthy part. So I refer you to see the video on plotting of displacement diagram on when the follower moves with simple harmonic motion by Mr. Ujjwal Rane, or you can see many videos are available on YouTube how to plot the displacement graph when the follower moves with simple harmonic motion. There are various videos available. Even you can refer the videos on the motion of the follower moving with simple harmonic motion. When the cam profile is made, only you have to concern about the displacement graph. So displacement graph will be plotted like that. So N is 150 rpm, S is 35 mm, theta O is 60 degrees and theta R is 90 degrees. In the description of this video I will post the link of Mr. Ujjwal Rane and some other videos which will be useful while plotting the displacement graph. So this is the given data. Now angle turn during outstroke is 60 degrees, angle turn during return stroke is 90 degrees. So this is given in terms of degrees. Better you calculate it in terms of radians, means you multiply it by pi by 180 and 8 by pi by 180. So you will get the angle turn during outstroke and return stroke in terms of radians. So that will be useful in the numerical part. So theta O comes as 1.047 radians and theta r comes as 1.57 radians multiplied by pi by 180. You will get these values. So theta o is 1.04 and theta r is 1.57. So calculate the angular velocity as is angular speed is given. You can easily calculate the angular velocity. Put n as 150 rpm. So angular velocity comes as 15.7 radians per second. So the displacement graph will look like this. This is the complete displacement graph. The outstroke angle, dwell angle, return stroke angle. This is the displacement. So the outstroke angle, then this part is called as rise. This is the dwell part and this is the return part. Remaining part is dwell. You need not to plot the remaining dwell part. So displacement graph, you have to, for displacement graph you have to see some other videos, and I had told you you can search this term on the YouTube. You will get to Mr. Joel Rani's page and you can see how to plot the displacement graph. You can see some other videos also, so that you can get clearer picture that how to plot displacement graph when the follower moves with simple harmonic motion, as it is a detailed part. So that's why I won't cover it in this session. So velocity of the follower moving with simple harmonic motion during outstroke. Its formula, as we had discussed in our earlier video on the SHM, its formula is pi by theta o into s by 2 into omega into sine of pi by theta o into theta. You need to remember this formula. Now we have to calculate the velocity at three different positions: at the start of outstroke, at the half of outstroke, and at the end of outstroke. So at the start of outstroke, that means theta o is 0, that is angle turn during outstroke is 0, that is theta is 0. So if theta is 0, theta, that is this variable is 0, if you put 0 over here, then this entire term, trigonometric term, will become 0, that is pi by theta o into 0. So that will become sine 0. As sine 0 is 0, so in this entire term will become 0. So you can directly put velocity at the start of outstroke, that is theta equal to 0 is 0. Now at the half of outstroke, at the middle of outstroke. So at the middle of outstroke, when angle turn is theta o by 2, so theta, you will put theta as theta o by 2 over here. So sine of pi by theta o into theta o by 2, theta will get cancelled. What will remain is sine of pi by 2. Sine of pi by 2 or sine 90 degrees is 1. So this entire part, trigonometric part, will become 1, and what will remain is velocity equal to pi by theta o into s by 2 into omega. So pi by theta o into s by 2 into omega, this will remain, and this trigonometric part will become 1. So I refer you that while solving any question on velocity, acceleration or jerk, first see whether this trigonometric part will become 0 or not. If it will become 0, so your calculation part will become simple. Even if it will become 1, then still you need not to write this part, you need not to calculate this part, only you have to calculate for the remaining part. That's why while starting the calculation, you first concentrate on the trigonometric part, whether it will become 0, it will become 1 or some other value. So here it will become 1, that's why velocity at the half of outstroke or at the middle of outstroke, it will be 1. It will be like this, multiply by 1. So put all the values, pi by theta o into s by 2 into omega. So put all the values, pi by theta o into s by 2 into omega. Again here theta o is 60 degrees and it is multiplied by pi by 180. As we had calculated earlier, it is 1.047. So you can put the value directly 1.047 over here instead of 60 into pi by 180. 1.047 will be sufficient and it will be easier for your calculation. So velocity will come as 824.25 mm per second. Let's calculate it in meter per second. So it will be 0.824 meters per second. Now at the end of out stroke, so this is the middle of out stroke. Now next third position is at the end of out stroke. Velocity at the end of out stroke means when theta is equal to theta o. So when you put theta as theta o over here in this equation, so it will become, the trigonometric part will become sine of pi by theta o into theta o. Theta will get cancelled and it will become sine pi. Also what you can do over here is just draw a vertical line over here and only solve the trigonometric part over here, that is sine of pi by theta o into 0 in first part, sine of pi by theta o into theta o by 2 over here, so this will become sine pi by 2, and in the third part sine of pi by theta o into theta o, so it will become sine pi. And as we know that sine pi is 0, so this trigonometric part will become 0 as it is in multiplication with other factors. So the velocity at the end of out stroke will become 0. Only one thing you should do is draw a vertical line over here and calculate only the trigonometric part over here at the start, at the middle and at the end of out stroke. So at the end of out stroke, velocity will become 0. One thing you should observe here is in any type of motion, whether it is uniform acceleration retardation, simple harmonic motion, or cycloidal motion, or uniform velocity motion, velocity at the start and at the end of out stroke is always 0. Only you have to calculate velocity at the middle of out stroke. So if you remember this, the start part and end part calculation will become simple, that is it is directly 0. Only you have to calculate for the half of out stroke. So if it is out stroke, then next part is return stroke. Velocity of the follower moving with simple harmonic motion during return stroke. So the only difference between outer stroke and return stroke is theta o becomes theta r and positive sign becomes negative sign, because the velocity during out stroke, if you take it as positive, then during return stroke it will be considered as negative, because velocity is a vector quantity. It only indicates the direction. Out stroke is outward direction, so return stroke is return direction. That's why minus sign indicates only the direction over here. Again, this part, that is trigonometric part, simply draw a line over here and calculate this trigonometric part for the start, middle and end of return stroke. As I had spoke earlier, that at the start of out stroke or return stroke, at the end of out stroke or return stroke, velocity will always be 0. As you put 0 over here, so it will become sine 0, entire term will become 0 and velocity will become 0. So at the start of return stroke, velocity will be 0. Only you have to calculate the velocity at the middle of out stroke, that is at theta is equal to theta r by 2. Put theta r by 2 over here, so it will become sine of pi by 2. Sine pi by 2 is 1, so only this part is remaining, that is minus pi by theta r into s by 2 into omega. Put all the values. Theta r, put the value in terms of radians, it is 1.57, so put the value over here. Instead of putting in terms of degrees, you can put it in terms of radians, so it will be simple. As this theta r is out of trigonometric function, you must put it in terms of radians. As in earlier calculation, it was theta o, so theta o was out of trigonometric function, that's why we had calculated it in terms of radians. Theta r is also in terms of radians because it is out of trigonometric function. Put all the values and calculate velocity at the half of out stroke, so it will be 549.77 mm per second. It's I forgot to put minus sign over here, so convert it into meter per second, minus 0.549 meter per second. Its sign is minus, please note it down. It is minus 0.549 meter per second. Velocity at the end of return stroke, so as we had discussed earlier, it will be 0, because here instead of theta you are going to put theta r. Theta r will get cancelled and it will remain is sine pi. Sine pi is 0, so the entire term will become 0. So velocity at the end of return stroke, it will be 0. Next is plotting of the graph. So At the start velocity is 0, on the y-axis there is velocity, on the x-axis there is angle turn. So this part is out stroke, this is the dwell, and this is return stroke. So at the start velocity is 0, at the end velocity is 0, at the half of out stroke velocity is 0.824 meter per second. Similarly for the return stroke velocity, at the start 0, at the end 0, at the half of return stroke it is minus 549. You won't put minus sign over here because graphically we had plotted it below the x-axis, that's why you need not to put minus sign over here. So plot the graph like this. It is a smooth freehand curve for the out stroke as well as smooth freehand curve for the return stroke, so during simple harmonic motion. Now acceleration part. So acceleration formula is, it is differentiation of velocity formula. So if you remember velocity formula, directly differentiate that formula, you will get acceleration formula. So pi square upon theta o square into s by 2 into omega square cos of pi by theta o into theta. So calculate the acceleration at 3 positions: at the start, at the middle, and at the end of out stroke. As there is a trigonometric part over here, so plot a straight vertical line over here and calculate the trigonometric part over here only. So let's start. At the start of out stroke means angle turn during out stroke is 0, so theta equal to 0. If you put theta equal to 0 over here, so it will become cos 0. Cos 0 is 1, so cos 0 is 1, that's why only this part is remaining. So pi square upon theta o square into s by 2 into omega square. Put all the values. Theta o you can put in terms of radians, that is 1.047, or you can put in terms of degrees, 60 into pi by 180. So it has been put as 60 into pi by 180. So it is in degrees into pi by 180, that will become radians, bracket square. So pi square upon this term into s is 35 mm divided by 2, omega we had calculated as 15.70. So put all the values and you will get the answer in terms of mm per second, because this displacement of the follower is in mm. If you had already calculated it in terms of meters, that is 0.035 meters, then you will come back at the direct value of 38.82 meter per second. So in both way you can do. Okay, now next is acceleration at the middle of out stroke. So at the middle of out stroke, that is theta o by 2. When you put theta o by 2 over here, so theta o will get cancelled and pi by 2 will remain. You are calculating over here on the right side of your sheet. So cos of pi by 2 is 0, as it is in multiplication with other factors. So acceleration will become 0 at the half of out stroke. So acceleration will be 0 at the middle of out stroke. Right? Now at the end of out stroke. So at the end of out stroke, the formula is same, you can remember here. At the end of out stroke, so put theta is equal to theta o. So theta will become theta o and theta will get cancelled. What will remain is cos pi. Cos pi is minus 1. So minus will be multiplied by pi square upon theta o square into s by 2 into omega square. So this formula is same with at the start of out stroke with the end of out stroke. Only difference is with minus sign. So we had already calculated this value, only you have to put the minus sign at the end of out stroke. So there is only difference of minus sign. Calculation was already done. Directly write the values, and minus 38.82 meter per second square. Its unit is meter per second square. Acceleration of follower moving with simple harmonic motion during return stroke. As we had seen during out stroke, it was plus minus acceleration. So during return stroke it will be minus plus. That means at the start of return stroke acceleration will be negative, at the end of return stroke it will be positive, and at the middle of return stroke it will be 0. So at the start of return stroke means when theta equal to 0, put 0 over here. it will be cos 0. Cos 0 is 1, that's why only the remaining part will be left. So put all the values. Theta r is 1.57 here in terms of radians. Remember, it is in terms of radians, 1.57 radians. Put all the values and you will get the value, that is minus 17,271.80 mm per second, as 35 is in mm, converted into meter per second square. So it is minus 17.271 meter per second square acceleration at the start of return stroke. At the middle of return stroke it will be 0, as we had discussed earlier, and at the end of return stroke it will be the same value of outstroke but with different sign. So it will be positive pi square upon theta r square into s by 2 into omega square. It is plus 17.271 meter per second square. Now next part is plotting of acceleration graph. So at the start of outstroke it is 0, at the middle of outstroke it is, at the start of outstroke it is 38.13, at the middle of outstroke acceleration is 0, at the end of outstroke acceleration is 38.13 meter per second square. So you have to choose a suitable scale for each graph. For displacement graph it will be different scale, for velocity graph it will be different scale, for acceleration graph it will be a different scale. On y-axis, on x-axis it will be same, that is theta, that is angle turned by the cam. On y-axis there will be different scales for different graphs. So at the start positive, at the half it is 0, at the end it is negative. Similarly during return stroke, at the start of return stroke there is certain constant negative value, at the half of return stroke it will be 0, and at the end of return stroke it will be positive value, that is 17.27. Let's plot it with the smooth curves. So smooth freehand curve at the start passing from the middle till the end, at the start passing through from the middle till the end. Jerk of the follower moving with simple harmonic motion during outstroke. So if you remember the velocity formula, you differentiate it, you will get acceleration formula, and once again if you differentiate acceleration formula you will get the jerk formula. So it is minus pi cube by theta o cube into s by 2 into omega cube sine of pi by theta o into theta. So we have to calculate it at 3 different positions, at the start, at the middle, and at the end of outstroke. So at the start of outstroke the angle turned is 0. So put theta is 0 at the start of outstroke, so it will become sine 0. Sine 0 is 0. So jerk at the start it is 0. At the half of outstroke means it is theta o by 2. So pi by theta o into theta o by 2. Theta o will get cancelled, and what will remain is sine of pi by 2 here. On the trigonometric part, sine pi by 2 is 1. So only this multiplication factor will remain into 1. So at the middle of outstroke only the multiplying factor will remain. Put all the values, you will get the value. Theta o, here it has been put in terms of degrees, that is 60 degrees into pi by 180, so it becomes radians and whole bracket cube. So you should remember this, whether you are putting it in terms of degrees or radians. You can either put it in terms of radians as 1.047 radians, and you need not to put this entire term over here, into 35 by 2, so it is 35 mm into angular velocity. So its value comes as this much mm per second converted into meter per second. So it is 1828.52 meter per second cube. So it is meter per second cube, as it is third differentiation of time with respect to time. Now jerk at the end of outstroke. So at the end of outstroke, that is velocity jerk when theta theta O. So put theta equal to theta O over here. Theta O will get cancelled. What will remain is sin pi. As sin pi is 0, so the entire term will become 0. The jerk of the follower moving with simple harmonic motion during return stroke. So during out stroke its formula is positive. So during out stroke its formula was negative. So that's why during return stroke its formula will be positive and theta O will become theta R. These are the only two differences, as jerk is a vector quantity. So jerk at the start of return stroke. At the start theta is 0, so put 0 over here. So sin 0 will become 0 and the entire term will become 0. So at the start jerk will be 0. At the middle of return stroke it is theta is equal to theta r by 2. So put theta as theta r by 2 over here. So it will become sin pi by 2. Sin pi by 2 is 1. That's why only the multiplying factor will remain, multiply by 1. So pi cube by theta r cube into s by 2 into omega square. Sorry, omega cube into omega cube. So put all the values over here. Theta r is put in terms of radians, 1.57 radians over here. Put all the values and you will get the answer. So jerk at the half of return stroke comes as 542.609 meter per second cube. Jerk at the end of return stroke, so at the end means theta is equal to theta r. So put theta is equal to theta r over here. So theta r will get cancelled and it will remain is sin pi. Sin pi is 0, so entire term will become 0. So jerk at the end of return stroke will become 0. So let's plot it. At the start jerk is 0. At the end jerk is 0. At the middle of out stroke jerk is negative. So 1828.52 meter per second cube. So at the middle it is certain constant negative value. At the start of return stroke it is 0. At the middle of return stroke there is certain constant positive value of jerk. At the end of return stroke it is again 0. So let's plot it. So we had plotted it and draw with a smooth freehand curve like this for during out stroke, and during return stroke the jerk will be represented like this. But one thing you should observe here, there is a vertical line over here, and as jerk is differentiation of acceleration with respect to time, that means it is the slope of acceleration graph. So the slope of acceleration graph during this part, as it is a curve over here, it is a curve over here, so slope is varying. That's why we had plotted with the help of a smooth curve instead of straight lines. But here it is a vertical line and slope of vertical line is infinity. That means at the start of out stroke there was 0 acceleration, and suddenly within no time it reaches certain constant positive acceleration. Means at the start of out stroke infinite amount of jerk is required to achieve this constant acceleration. That's why at the start of out stroke constant jerk is infinite amount of jerk is required. Similarly at the end of out stroke there is certain constant negative acceleration or retardation was present, and suddenly it becomes 0 within no time. So there is a vertical line. As the slope of vertical line is infinity, that means infinite amount of jerk is required to achieve 0 acceleration from certain amount of constant retardation value. So infinite amount of jerk is required at the end of out stroke. Similarly at the start of return stroke there is a vertical line. That means infinite amount of jerk is required at the start of return stroke. At the end of return stroke again there is a vertical line. That means infinite amount of jerk is required at the end of return stroke to achieve this constant positive value to 0 value over here. So it is infinity at the end of return stroke. So jerk is infinite at the end of return stroke. That's how we had plotted displacement graph, velocity graph, acceleration graph and jerk graph for the follower moving with simple harmonic motion during out stroke as well as during return stroke. So this is the complete velocity graph, acceleration graph and jerk graph for the follower moving with simple harmonic motion. Thank you.